All right. If I sound a little better, it's because I have a new microphone. I got to step up my game in the YouTube industry. So, don't forget to hit subscribe to my channel. More technological advances coming soon. But right now, we need to talk about the washer method. That's right. Now, the washer method, I kind of prepped it from the last one. If you watched the last video, and if you haven't watched the last video, you might want to hit the notification bell while you're at it so you don't miss any new content. All right, got that in. So in the last video, I talked about the disk method, right? So it would probably be helpful to know the disk method before you understand the washer method, because the washer method is just the disk method kind of twisted a little bit. So at the end of last video, the question I raised is, what happens if there's a gap in between the region I'm rotating and the axis that I'm rotating around? Disk method doesn't really have an answer for that. Disk method has got the cross section is a solid disk, so there's no holes or anything. So the washer method is going to answer that. So here's two ways to think about kind of what is happening with this washer method. One way to think about it is this picture right here. Not unlike the hole minus hole, like the W hole minus the H hole, like the big thing minus the small thing. So if you take a big thing and subtract out, you bore out this red shape, you get that weird looking little doohickey over there. Right, so it's like one disk method minus another disk method. But there's a different way to think about it, in a way that I kind of like better, because it gets back to the idea of cross sections. This whole volume routine has involved looking at the shape of the cross section of the solid and just integrating that area formula. So if we could look at that same figure and like stand there and just X-ray vision that thing, we would see through the like a what is it, MRIs kind of do the same thing with your brain. I'm not sure what they would find with mine. But if we could do that with this shape, right, we would see these like washer shapes all the way through that solid. So the cross section being a washer, that's why this is called a washer method, it's just two disk methods put together. So what we want to do to find the volume of a solid formed when a planar region that is non-adjacent to the axis of revolution is rotated around that axis. We use this formula over here. And you might see how that is just two disk methods put together, one minus the other. So we need a big radius squared and subtract a small radius squared. Now this is this representation in terms of x. That's when we rotate around a horizontal axis. We're going to have to kind of make some decisions here about who's the big radius and who is the small radius. So it really is helpful to draw. But the drawings that you're about to see, they get a little messy, right? They get a little bit messy. So sometimes it's helpful just to look at the two-dimensional region without trying to draw the 3D version. So it's a little bit more clear as to which one is the big radius and the small radius. Again, I can't do the thinking for you. I wish I could. Actually, I don't want to do the thinking. You do the thinking. That's what makes math so fun. It is like how we get to think through it. We get these formulas and these structures on how to do things, but then we can get some really cool problems that we've got to really figure out how to do them. And that's what makes math so awesome. That's why I love it, is because no problem is like any other problem, or there's problems that are similar, but there's a twist in one of them. Anyway, the distances, big R and little r, they're going to be that old top minus bottom routine. So again, function minus axis or axis minus the function, depending who is top and bottom. And then, of course, if we're in terms of y, we'll be right minus left to get a horizontal distance. All right, so here's the first example. I'm going to take the region that we saw in the other video. It was the region bounded by the x-axis, x equals 4, and then square root of x. We're going to rotate that this time around the line y equals 1. So you can see over here that the region and the axis, there's a separation, right? There's a gap there. So this method is really not good for this one. We need this washer method because when we spin that around, there's going to be a hole all the way through the middle that we'll have to subtract out. Okay, so you can see how I've drawn here on this without drawing any 3 dimensions going on here. The big radius is going to be the distance from the axis to the thing that is furthest away. So the thing that is further away from the axis is the function y equals root x. And then this little small radius over here, the distance from the center, from the axis, to the closer part of the region, well, that was just the x-axis. So that distance is always 1. So when we set up our integral, so when we look at this 3-dimensional representation of what's, as I told you, it was going to be, there's a lot to look at over here. So when we spin that around y equals -1, we need this formula, pi times the integral from a to b of big radius squared minus little radius squared with respect to x. Big radius is the distance from root x to -1. So top was root x, bottom was -1. So the distance there is root x minus -1, or root x plus 1. And then the small radius, which we've already talked about, is 1. So we put those together into the formula over here. We know where the limits, because this region lives on 0 to 4 in terms of x. So we have a way to calculate the volume. That would be pi times the integral from 0 to 4 of the quantity root x plus 1 squared minus 1 squared, which is just 1 on that other part. But it's important that when you set up washer method, you have big radius squared minus a little radius squared. You don't want just one thing squared. You don't want big radius minus small radius, and then you need each individual radius being squared because it's 2 disk methods, one subtracted from the other. Okay, same region rotating around something above it. So y equals 5. So that's horizontal line, that's terms of x. That's washer method, right? We got a big gap there in between the axis and the region. So we need washer method, right? So here is the 3-dimensional rendering of what this thing looks like. I mean, it's like a cylinder with this like lampshade cut out of the middle. Regardless of what it looks like and what you can relate it to in your household, to find the volume, we need the washer method, right? So pi times the integral big radius squared minus little radius squared. We just got to determine the lengths of big radius and small radius. So big radius, that's the distance from the center, right? The center of rotation, always from the center to the piece that's furthest away. Now the piece that's furthest away, look at the picture up there. The center, y equals 5, to the furthest piece away. So the distance between 5 and the x-axis. Well, that means the little radius is always 5. Okay, now the big radius is always 5. The little radius then is the distance from the center, always from the center, to the closer boundary of that region, which is root x. So the little radius is going to be 5 minus root x. So there's all that taken care of there. We got big radius, small radius, pop it all together in the washer method, and we get this integral. Pi times the integral from 0 to 4 of big radius squared, 5 squared, minus the quantity, 5 minus root x squared, times dx, and then I calculated it on Desmos if you really wanted to know, or you try to do that in your head or something. I don't know, but it's there. Okay. In terms of y now. Same region. This time we're going to rotate it around the y-axis. So The rules are pretty simple. If you're rotating around a vertical axis, you need to be in terms of y. So that means we're going to have to do some manipulation, right? This is x equals root, y equals root x. So x equals y squared would be the function. X equals 4 is the right side. Y equals 0 is the bottom side. We're going to spin this thing around the y-axis. So maybe you can already picture what the big radius and the small radius is by looking at this two-dimensional region. Maybe, maybe not. So let's look a little. Whoa, there is a three-dimensional rendering of this thing. If you've ever been to a mall or you've been to the zoo here in town and you got that coin thing that you always put the coin in and it like spins around and then it drops down in the bottom. That's kind of what I see here, like one of those little funnel things. What is the volume of it? Okay, so we clearly see this empty hole, this gap in between the region and the axis of revolution. So we need an in terms of y washer method. So you see the generic setup there. We got to come up with the big radius and the small radius. The big radius is the distance from the center, always from the center to the boundary of the region that's the furthest thing away. And that will be x equals 4. So the distance between the y-axis and x equals 4 is always 4. That's the big radius. Small radius time, that's from the center of rotation, so the axis, y-axis, to the closer boundary. Well, that's x equals y squared. So y squared being on the right, y-axis being on the left, we know what the little radius is. It's y squared minus 0. So here is all of that information right there. Big radius in terms of y, little radius in terms of y, and then we put it all together there. So the volume of that funnel, the coin receptacle, would be the integral from 0 to 2, because this is in terms of y, that region lives 0 to 2. Of big radius minus small radius, so 4 squared minus y squared squared. I know that's y to the 4th. I know, simplify to your heart's content, but I'm just subbing them into the formula right now. And then multiply that thing by pi, and you get approximately 80.425. Big deal, right? It's the setup that you're here for. Okay. New region. G of x in red is e to the x. H of x in blue is x plus cos x plus 1. Now they intersect at those two spots. And rounded off, those are, you see them there. Now, you probably want a little more accuracy. If you're going to do this on any kind of AP exam or anything like that, you probably want to get these a little better accuracy. Your calculator can handle a little more accuracy than, say, Desmos, which is where I got these intersections. But if you're just trying to get a quick answer, Desmos is great, and it'll give you relatively good accuracy. So we're spinning around the x-axis, by the way, if you didn't hear me say that, or I didn't say that before. We're going to spin around the x-axis, that region there. And we're going to have to use something in terms of x. So we're spinning around a horizontal axis. So we need terms of x. There's a gap. There's a clear space in between the region and the axis. So we need this washer method, which you can see the skeleton of over here. I need big radius. I need small radius. The big radius is the distance between the center, always the center, to the furthest boundary, which would be the blue function way up there. So h of x. So that vertical distance is top minus bottom, h of x minus 0. So it's just h of x. Well, what about the little radius, huh? What about the little guy? Well, the little radius, that's the distance from the center of rotation, always the center of rotation, to the boundary that's closer, which is the red function. So the little radius in terms of x is g of x minus 0, which is just g of x. Sub in what you need to sub in. There it is. And then the A and B are the two intersections that I had before. So then pi times the integral from A to B of h squared minus g squared. And that would give you a little bit more than 12 if you care about that. So the setup is good. So washer method is it's not, if you know disk method, washer method is like not crazy. It's the same types of thinking. It's figuring out the length of a radius that is from center, always the center, to the thing that's being rotated. Now, whether that's closer or further away, that's another layer of thinking you've got to do with washer method. When there's a gap between the region and the axis, that's when I need to use this washer method. Cool. So I'm going to do this a little bit different here. Let's play Jeopardy. So I'll take things I learned in calculus for 400. No longer Alex. It's 2021 right now when I make this. Alex Trebek. R.I.P. He was the man. All right. So here's the clue. Here's the clue. The integral expression below gives the volume of the salad where the region is rotated about this line. Check it out. Can you figure it out? Yep. Okay. The Far Side is great. Oh my gosh. I hope you guys know Far Side, that cartoon. Big props to Far Side, the cartoon. But this dude is right. Even though he's getting blown out by Thomas and Albert there, he's right on this one. It is y equals 10. We're rotating that region about the line y equals 10. Then the big radius would be 10 minus g, and the little radius would be 10 minus h, and we could sub those into those spots. So it's possible to work forwards and backwards given a region and an axis, setting up an integral, or you could even dissect an integral that's already been created, and you can figure out what things have been spun around. So that's just another way to think about it. As we wrap up this lesson on washer method, here's those formulas again one last time. So it's just a big radius squared minus a little radius squared. That's what you need, is the big thing about washer method. So thus ends our unit on volume. Now, to be honest with you, there is another way to find volume. And it's called shell method. And I really wish we had time in this weird school year to talk about it. It's no longer part of the curriculum according to AP. It's 2021, right? It's 2021 right now. So maybe in the future, the AP exam will include shell method back into its BC curriculum. But AB, you're good. You're done. All right, you don't have to do shell method. Maybe AP is going to put it back in there. I would love to show you about shell method. I wish I could, but you can research that if you want to. Maybe I'll pop another video on here just for good measure, just for fun. But next time we get into Big Idea 6 and we start adding up an infinite number of items. Infinite series is coming. Get ready. It's going to be fun. Peace.